Hello and welcome. In this lab demonstration, I've set up an environment in GNS3 where we're going to use route maps, where we apply them to routing protocols in order to manipulate traffic. So in the previous lab, for those that haven't been following along, we used route maps and applied them to interfaces in order to control and manipulate traffic. And we discovered some of the limitations of doing that. So now we're going to be using a slightly different configuration in order to try and troubleshoot some of the potentially common issues that you could run into. So on the screen you can see there are some rectangle boxes, and those are indicating the routing protocol that's running. So any of the interfaces that fall within the box are within that routing protocol. So we've got OSPF, EIGRP and RIP. Now, if you don't know what route redistribution is, it's okay, but you will eventually have to learn. You definitely know what it is if you want to pass it, the ENARSI exam. But if you don't, it's okay. I'll just give a brief overview, and then you can learn more about it in detail at a later time. So, if we look at router 2, we can see it's actually running the RIP and EIGRP protocols, and I have it so that it's using mutual redistribution, which means the RIP routes are being redistributed into EIGRP and vice versa. So all of the EIGRP known routes are being redistributed into RIP. So that basically router 1 over here, which only knows RIP, is aware of all of the EIGRP routes, which also include all of the OSPF routes, because router 3 and router 4 are redistributing OSPF into EIGRP and vice versa. So both of them are doing what we call mutual redistribution. So just a little bit more of a background on what we have here before we go into it is every connection between the devices is running in the format of 10.0.x.y as a /24. And the X is indicative of the numbers of the devices. So, for example, this connection between router 5 and router 6, it will be 10.0.56 because those are the other two devices. And then for the final octet, for the interface, that just matches the number of the device. So for this interface out of router 5 pointing to router 6, it would be 10.0.56.5. So that's how it's all set up. Now all the devices also have a loopback interface running, which matches their number, but the only one we're really concerned about for this demonstration is the loopback 0 down here on router 1. So pause the video if you need to properly absorb what you can see on the screen. Otherwise we'll get started straight away with what we might be running into when it comes to issues and problems to troubleshoot. So I'll start with opening up a console here on router 2. So I'm just going to do a show IP route so you can have a look at everything router 2 knows about. And you can see it knows quite a lot. There's many things listed here, and the main one we're going to be focusing on is this route to 1.1.1.1. So it knows about it through RIP via that next hop address of router 1. So down here, that's exactly as you would expect. So let's just do a ping to that address and just make sure it's all happy days, and the trace is definitely going to go straight to that next hop as well. Excellent. So that's all working as we would expect. Now the issue might come to light when we go into router 3 and router 4. So I'll just open up a console into both of those. So I've already configured all the devices. Everything is configured correctly as you would normally configure route redistribution and routing protocols. So I haven't done anything funky to inject an error here. This is actually default behavior that we're about to see. So if I do show IP route, this is on router 3 over here. So it knows about that route via, so it's an external EIGRP route via router 2. So if it gets traffic destined for that network, it will send it down router 2, that's good. That's what you would expect. And if we go to router 4, I'll just show IP route, we can see that it actually knows about it through OSPF. OSPF external type 2 has an even lower admin distance than router 3, and it knows about it via router 6. So router 4 is looking to router 6 in order to reach this network down here, which is not what we want. We would expect it to go down this path, router 2 to router 1, but it looks like it's going to go 4 to 6, 5, 3, 2, and 1. And instead of checking every device, we can confirm that by just doing a trace to that address. And we can see here, looking at the last octet, it goes 65321. 65321. So that's obviously not ideal. And the reason it's doing that is just because of the way that the mutual route redistribution works when you're using EIGRP and OSPF in this manner. Because if you recall to that first lesson we went through in admin distances, recall that EIGRP has a lower admin distance than OSPF, but only for internal. So internal EIGRP routes have an admin distance of 90, but external have 170, which is why on router 3 we can see it has 170 here. Right? But OSPF doesn't care if it's internal, external type 1, external type 2. They all have an admin distance of 110. So what's happening is, because we've got mutual redistribution on both of these devices, it's advertising the EIGRP known routes into OSPF, but when it does that and advertises any known routes from here into here, it's changing the route to an OSPF external type 2 route, like we see on router 4, OSPF external type 2. So although previously we learnt about it through EIGRP and it had a 170 admin distance, as soon as we redistribute it into here, it becomes 110. So the admin distance is lowered once it's changed and redistributed into OSPF. Okay, so what actually ends up happening when you first turn on these devices, what you can run into is, it's kind of like that Spider-Man meme where there's the two copies of Spider-Man looking at each other, pointing at each other. So router 3 and router 4 can both look to each other as the correct path or destination to reach that network 1.1.1.1. Because let's say they both learn about this route over their respective links to router 2, they'll then advertise it into OSPF with that 110 metric, which will then be redistributed from router 5 to router 6, and then from this way up to router 6 from 4, goes from router 4 to 6 to 5, and so eventually router 3 hears about this 1.1.1.1 network, and router 4 hears about the 1.1.1.1 network from their respective partners through OSPF, and it already knows about it, but through its router 2 links, but it knows about it with an admin distance of 170. So when it hears about it from its partner through OSPF, it's getting a better admin distance, so it'll replace it, and they'll end up just pointing to each other as the best path, and it'll just keep going back and forth. Now thankfully there are some solutions in these devices to eventually try and rectify itself, and that's what's happened here. Is router 3 has gone, nah, this is stupid, we're just going to keep sending things back and forth, so it's now left its connection all the way down to router 1 through OSPF. So if we look on router 3, that's why up here it's got this path which has a 170. Now it's probably heard about it on a 110 admin distance from router 4 via router 6 and 5, but it has dropped that advertisement because it's probably timed out when it's tried to maintain a connection or to contact this network. So I've run through the simulation or this emulation a few times, and sometimes they will actually both come up pointing to each other in the route table, but then eventually you lose a neighbor adjacency in OSPF, and then they re-establish, and eventually this is the result. One of them will actually point to the ERGRP path, while the other one just points to the partner taking the long path. So this is not ideal. What we want to do, so without going too far down the track with route mapping, with route redistribution, we want to actually learn how we can fix this with route maps. So we are going to look at what we can do to manipulate the traffic in the routing protocols to make sure that both of these devices, router 3 and router 4, go directly to router 2 in order to reach that 1.1.1.1 network. Alright, so let's move on into the actual route maps. Okay, so moving into the route maps, this is going to get a little confusing, so make sure you're ready to properly apply yourself. Get your distractions out of the way, because it can get a little bit tricky. So what we're going to do is use route maps to tag traffic, and then we're going to deny that traffic in certain locations. So what we want to do, because right now router 4 is going this long path via 65321 to reach that final destination. So what we could do is on router 3, as we advertise into OSPF, tag the traffic, and then once it reaches router 4, we'll just deny, saying we don't want it. That way, we're forced to go via the other routes that we have through ERGRP, making the shorter path. Right, so that will fix the issue. But if we do that, router 6 is still going to take that one extra hop. It's still going to take that longer path to reach the final destination. So it's not ideal. What we would have to do is also on router 6 do the same thing. If we receive it with that tag, then deny. Okay, so this is where you're going to have to really pay attention, but first we'll just do the start, where we just tag the traffic on router 3, and then we can move on. So at the very first thing I'm going to do is just make sure we're still following that same path to 1.1.1.1 on router 4. So if I do a trace to that destination, we can see we're going router 65321. 65321. Okay. So let's fix that by going into router 3 first. Okay, let me just clear all that. So we're going to go into configure terminal, and now we're going to create a route map as the first thing. Sorry. We're going to create a route map as the first thing we're going to do. I'm going to name this one ERGRP to OSPF, because we're going to apply this route map to all of the ERGRP routes redistributed into OSPF. Now I can type in permit 10, but that happens to be the default behavior as well. So if I specify nothing, it's the same as writing permit 10. So I can do that. Now, I don't need to specify anything more specific with the match statement, because we're already only applying this to ERGRP traffic redistributed into OSPF once we do that, which we'll do after. So I don't need to be more specific with match. I can leave that with matching everything. Remembering default behavior for match is all prefixes. But we do want to set a tag. Now you can choose any number. I'm just going to choose an arbitrary number of 99. Okay, so that is done. All happy days. Now if I go into the router process, that's where we do the redistribution and add the route map. But I'll just show you what it looks like right now. So if I do this, we can see that I'm running router process OSPF. Sorry, let me say it again. Router OSPF process 1, and we have this redistribute ERGRP 500 subnets. So now we're going to use the same command, but we're going to apply the route map traffic. So essentially, it's going to do the same thing, but now tag that traffic with a route map. So if I go to router OSPF 1, I probably have to spell it correctly, right? Router OSPF1. Now, redistribute, ERGRP, Autonomous System 500, all subnets. Now we can see we have the option of adding in extra keywords, one of which is route map. Then you specify the name of your route map, and the name we created before was ERGRP to OSPF. And then you go back to the same options as before. So that's all you have to put in. Now it's done. So now, if you look on our topology here, router 3 is redistributing ERGRP into OSPF, but every time it does, for that traffic specifically, it now has a tag of 99. Now we haven't configured any other device to do anything with tag 99 traffic, so we're not going to see any changes yet. But what we did want to do is make it so that router 4 didn't accept those routes, but it still accepts everything else. So now we're going to go into router 4 and do just that. So on router 4, let me just make sure, so show route maps, we can see we don't have any running. Excellent. So now let's go into configure terminal, and I am going to try and type correctly and create a new route map, but this time I'm going to call it tag 99. Alright, now the difference now is we're going to actually say deny, and you can type in sequence 10, or that's the default, so you don't have to, up to you, but make sure you put deny. And we do want to match something specific with this one, because we want to match the tag traffic of 99. Now for the set command, we don't actually have to do anything, because we're already performing what we want with this, the deny. So anything that matches is going to be denied. So I don't actually have to specify anything for set, and that's it. So exit. Now that's all well and good, but we have not associated this route map yet with anything. So we've defined it, but we're not actually using it anywhere. So what we're going to do is we're going to use it on router 4 on the OSPF process. So anything coming into OSPF, we want to deny that has a tag of 99. To do that, let me just show you what I'm currently running. So do show run section OSPF. So this is all we're doing at the moment. And I'm going to add in an extra command. So I'll go router OSPF1, and we're going to use the distribute list command. You can then see the options for keywords after that include route map. So distribute list, route map, and then the name of your route map. So for us on this device, it's tag 99. And then you have to specify whether it's traffic going in or out. And we're talking about traffic going into OSPF. And that is now done. So anything going from on router 3 from ERGRP into OSPF has a tag of 99. We haven't done anything on 5 or 6 with regards to that traffic, but now on router 4 we've set a route map that will look for tag traffic coming into OSPF with a tag of 99, and if it does have that tag, deny. So now hopefully router 4 is no longer going to know anything about this path to get to 1.1.1.1, and is now going to default to its secondary route of ERGRP external and start going via router 2. Now this is where you have to really pay attention. So if we do a show IP route now on router 4, we can see that it's indeed going via router 2 to get to that router 1. So on the surface it looks like we've probably fixed the issue with what we had before. And if I go back to router 3, I do show IP route. Unfortunately now on router 3 it is going via router 5, which will then go to router 6 and then go the other direction. So in router 3, if I do a trace, it's now taken that long path. So it's now going all the way around this way. Okay? Because router 4 is no longer knowing that it has an option to go this way for that traffic. So when it advertises, it's now advertising in saying, hey, to get to this, you can go like via me. And now router 3 is hearing about it now, and it's going, oh, well, that's got an admin distance of 110, which is better than my external ERGRP, so it's now taking this long path. Right, so now we have to make sure we do the exact same thing, but in reverse. So we're going to filter in from router 4 and block it on router 3. Okay, so I'll go through this one much faster, just so that we can save time. But on router 4, we'll just firstly do a trace to 1.1.1.1, make sure that goes through. Yep, that's as it should be. Now we're going to do the same thing we did before, but in reverse. So feel free to skip this if you want. Timestamp on screen to go through to the next stage. Otherwise, I'm just going to continue configuring this. So route map, we're going to use the same name as we used before. Route map to ERGRP to OSPF. And again, I don't need to specify this permit stuff. So there. And set tag, and this time I'm going to use 15. Got to use a different tag here. Exit. And now I'm going to go into the OSPF process and redistribute ERGRP 500 subnets route map and then ERGRP to OSPF. So that's done, and now I need to go onto router 3 and do the actual deny. So if I go router 3 and I go conft and I go to route map and I say tag 15, deny 10, match, tag 15, exit, and router OSPF 1, and we're going to say distribute list, route map, tag 15 in. Okay, so that is now done. Now we've done the same thing in both directions. So if I do a show IP route, we can see on router 4, it knows to go via router 2. And if we run the same command over here on router 3, it also knows to go via router 2. So now we have fixed the issue where both of these devices are now going to take the optimal path to reach that network. Let's just verify on router 3. Oops. And router 4. Excellent. Now let's just have a look on router 5 and 6 and see where they're currently pointing for this traffic. Okay, so show IP route, and on 5, show IP route. Okay, so router 5 is going via router 3, and router 6 is going via router 4. Okay, so thankfully the way that it's set up now is every device will now take that shortest path available to get to the 1.1.1.1 network. Let's just verify, so trace on 6 and a trace on 5. Okay, so excellent. This works exactly how we want it. So all happy days. But there is something else you have to understand. We have to cover. You need to understand this for your exam. So it's working right now because of the way that it's configured on these devices with these two protocols. So let's, for argument's sake, say instead of doing what I just did there, I said the same thing on router 3, set that tag to the traffic of 99, but on router 6, I stopped it here, so that router 6 had no chance of knowing to take this one extra hop to get to 1.1.1.1, and we denied it there. If we did that, there's going to be some weird behavior that you need to be aware of, and I'll actually show you right now. We'll do that. So on router 6, we're going to find the 99 tag traffic, and we're going to do the same thing we do on router 4. We're going to deny it. Okay, so although the network's doing what we want right now, this is essential that you understand. Let me just close that, go back to this one. So I'll just make sure that's all still working fine, and we'll do show IP route. Yep, everything's happy for that. We see all of our routes. Now I just wanted to make sure that you can see we've got all of our routes, because something's going to happen once I make these changes. So I'm going to define a route map, the same as I did on router 4, call it tag 99, and we're going to deny on sequence 10. Okay? Going to match the tag traffic of 99, and that's it. But now we're going to go into our router OSPF process, and we're going to use that distribute list, route map, tag 99 in. So the exact same thing we did on router 4, but we are going to see some different behavior. Alright, so now if I do a show IP route, all of a sudden we've lost almost all of our routes. We now only know about our connected and our local routes. Okay? We only know, so router 6 only knows about these directly connected things. It doesn't even know about this one here anymore. So it can't reach one, it doesn't know about 1.1.1.1. So if I do a trace to 1.1.1.1, it's just going to fail. It doesn't have any routes there. It doesn't have a default route, it doesn't have anything, right? So that's just going to keep failing. The reason that happens is because of the behavior of route maps when you are using that deny keyword. So if we do a show route map, this is what we're running. We're running a deny sequence on sequence 10, matching the tag of 99, and nothing set. It should be the exact same on router 4. Show route map. Except router 4 also has the other route map that it's running, because it's doing that reverse filtering all the way over to router 3. Right, but this for tag 99, it's the same. Deny on sequence 10. Okay. The difference here is router 4 can still learn about all the other routes through like ERGRP process. So that's how it still has routes to everything else. If we go on to router 6, what's happening on these devices in this route map definition is route map tag 99 deny on sequence 10 is looking for anything that matches this tag. So anything that's tag 99, we're going to deny. And then the default behavior is there's some implicit next sequence that it will move to. So if it doesn't match, so if the traffic coming into OSPF, which is where we've applied this route map, let's just verify that so you can visualize it. Here. So if the traffic coming into OSPF does not match this, then the route map moves to the next sequence. And the implicit next sequence, when you haven't specified, is just going to match this. It's going to deny everything. Well, it's going to be a deny sequence. Basically, imagine it's route map, tag 99, deny sequence 20. That's the default behavior. It's matching with nothing set, which means all prefixes. So the default behavior now is distributing into OSPF. If it does not match this tag on sequence 10, then it will deny everything else as well. So essentially, we are just denying everything into OSPF. And there's a very simple fix. You need to know this fix. This is essential. What we're going to do is going to use that same definition. Route map, tag, 99. All we're going to do now is permit on sequence 20. So now we're going to make the default behavior, instead of deny, permit on the next sequence. And now, remembering the default behavior for the match statement is to match all prefixes. It matches everything. So I don't have to specify everything, because that's exactly what I want. If it doesn't match tag 99 traffic, then I want everything else to be permitted. So now I can just exit. That's all I had to do. And now if I go to show route map, we can see we now have two sequences. sequence 10, which is deny, matching tag 99, and sequence 20, which is permit, matching everything. Because it says nothing, it means match everything. That's how route maps work. So now, if I do show IP route, all of our routes have come back. Okay, very important that you understand that. So when you're using that deny statement with route maps, understand that you need to, if you want to then continue permitting everything else, you need to add that second command at the end, which is just permit. So if you've already specified, let's say, sequence 10, 20, and 30 are all deny statements matching different things, then you would have to do permit on sequence 40. So on the next sequence, permit all. Just be aware that that is essential. And the reason that it's not doing that on router 4 is because it's running that ERGRP process. Okay, so on router 4, it's still got all these other ERGRP routes. Oops, apologies, let me delete that. So it's still running all those so ERGRP process, so it still knows about those. But what it's not going to learn is everything else from OSPF. So router 4, although it looks okay when you first do this, is actually missing some routes, right? So we also need to make that change on router 4, because router 4, if we look at something it would learn through OSPF, it would learn like 5.5.5.5 and this network here. If I go look in the routing table, we don't have that. See, 5.5.5.5 is missing. And if router 4 tries to ping it, it's going to fail. So the same thing is happening over here on router 4. We also have to add in that permit sequence. You really need to remember that in an essential part of understanding how route maps behave. So I'm just going to do that. I'm going to go to route map, and on that same one that we applied into our OSPF process, remember we have two route maps on this one. So we're looking at this, which is the tag 15. We're going to set permit 20. Sorry, not 15. This one will be 99. Because this one is in relation to the 99 tag traffic coming into the device from router 3. So I'll press enter and exit, exit, and now if we do a show IP route, all the other routes are back again. We can now see that 5.5.5. We can also see this one would be 10.0.35.0. Yep, through OSPF. So all of our OSPF routes have now come back. Alright, so remember that. That is a very important part to how route maps behave. And hopefully you now have a deeper understanding of how to configure and troubleshoot route maps. So let's just do a final verification. We'll go to router 6 and do a trace. And we'll go to router 5 and we'll do a trace. So it's going, so router 5 is going 3, 2, 1. So 3, 2, 1. And on router 6, it is going 4, 2, 1. 4, 2, 1. Perfect. Okay. So that is it for the route maps. I know it's been a hell of a lot to learn if you've never played with them before. Obviously you'll have to go in and play around yourself. It's probably not going to be enough just to watch these videos. And remember that there's a lot more when it comes to route maps that you could potentially do, and Cisco could potentially test you on. Especially when it comes to, we'll say blah. When it comes to the match statement, there's all these other things that you can match, and the set. It's a ton of different things you can set as well. Specifically when it comes to BGP, controlling BGP routes, there's lots of options in here for that. Otherwise, thank you for watching. Feel free to leave any comments and questions. Otherwise, throw a like, a thumbs up if you appreciated the video. Feel free to subscribe, and there'll be additional information in the description if you're after anything else. Hopefully, I will see you in the next one.